Okay, this is 610, 11, 12, 13 entropy, part 2. This is not too bad, not too long of a thing to just show you. Again, you could already right now probably do pretty much all the front of the worksheet. They had no math, but now I'm going to tell you how to do the math part on the back. Okay, so in the notes, first of all, in 611, they're going to talk about how they derive equations, why it's true, and we can do what we're going to do. It's kind of like in the gas law chapter. Remember we said PV and RT had to make these assumptions? Well, we did not show you all the calculations and math that derive PV and RT. And we don't have to worry about that in here either, about how you derive these equations. But it is kind of, there are some interesting facts to bring up in there, like some assumptions. In fact, it talks about in 611 the first and second law of thermodynamics. Law number 1 says the energy of the universe is constant. So energy cannot be created or destroyed. It can pass from one form to another, or to be transferred from one place, system, to surroundings, all that to another. But the total energy is the same. We talk about in our limited definitions of thermo to use for on Earth or in our science, the energy, we look at energy as being either Q or W, either leaving in the form of heat, flow, or work done by the system or on the system. And work pretty much in volume expansion is all we're looking at. So it's interesting, you can look through it. Oh, number 2 says, in any spontaneous process, there will always be an increase in entropy of the universe. That's why I said earlier, everything leads to chaos. Everything causes, anything that's spontaneous leads to chaos. Positive delta S for the universe. That's a neat thing. Well, that's how all these equations get in, how they derive it, and all this stuff going through these pages. And in your book, it will get even more in depth. But this is interesting to know, and something to look at as well. Entropy changes in the surroundings can be determined by heat flow. So, when everything comes down to it, and we're trying to figure out thermochemistry, we know that entropy can be seen as changes in volume, changes in, then we talk about the microstates, temperature changes. All this can lead to more entropy. Well, what's interesting is that we can ultimately measure entropy from heat. That's all. And it's not as much heat as the other, but like it talks about, if you have an exothermic reaction, then that means it releases heat. That means the surroundings will undergo an endothermic change. And for an endothermic chemical reaction, the surroundings will undergo an exothermic. So that's kind of a neat thing to look at. Well, okay, I'm just talking and talking. Like, what do we really need to know? What we really need to know is, we know that delta H is enthalpy. And it measures the unit. Think about the units for a moment. It was in kilojoule per mole. So whether or not something's endothermic, exothermic in a reaction, delta H enthalpy is measured in kilojoule per mole. Well, it turns out that entropy can also be measured in, but it's going to be, the units are going to be used are going to be joule per mole Kelvin. Kind of strange there. But first of all, notice this, joules and kilojoules. So when entropy is measured in the form of heat, how much heat is involved during an entropy change, it's very small compared to kilojoules, but under the conditions of thermo, the standard conditions, under the condition that the reaction must be at constant pressure, under those, entropy can be measured as heat. So that's the good news. So we're able to make calculations and predictions on that, and you will see that it's actually very interesting. The next lesson we get to will make more sense and can be more fun of this. So let me do letter A. It says, calculate the change in entropy. Oh my goodness, did I lose my note? Oh, hopefully I did not. Entropy. Calculate the change in entropy of the surroundings for the following reaction. And, oh, okay. You know what? I cannot believe this. And my computer, why does this have to happen? Mine had to go off. I'm sorry. I wish I could pause it right now. I'm trying to find something. But it looks like... Oh, you know what? I'm okay. Never mind. I'm on the wrong page. We're not doing that problem. We're not doing the entropy of surroundings. We're going to do this. 613. Okay. We're at 613 right now. All right. Good news. Yes. I don't have to worry about that. We'll be done quick. Okay. The third law of thermodynamics says the entropy of a perfect crystal is 0. I told you that. So at 0 Kelvin, a solid, everything will be solid in perfect crystal. Well, they create, it is a man-made property called the standard entropy. Standard entropy is the increase in entropy that occurs when a substance goes from 0 Kelvin all the way to 25 degrees Celsius and 1 atmosphere. In other words, to standard thermo conditions. When you go from 0 to that, this is a value that's assigned to every element. So remember, every chemical has its own delta H value, delta H of formation. Well, they all have their standard entropy values as well. And those values are, as I said, they're only theoretical because we can't get to 0 Kelvin. So here we go. The equation looks exactly like the one you saw for delta H. So that's good news. It says that for a chemical reaction, the entropy, the standard entropy change will be the sum of the entropy change of the products minus the sum of entropy changes. Oh, that's wrong. It should not be. It should not be change in entropy. It'll be the standard entropy of the products minus standard entropy of the reactants. Sorry about that. Okay, and of course, I always tell you put brackets around them, just like we did the other one, and even put in a little n for moles as well, because you are going to put moles in those equations. So you'll be like, hey, I've seen this before. The main difference is the unit for entropy is joule per mole Kelvin. In fact, maybe I'll just change that so you'll get a little reminder right there. All right, so here's what it says. One problem. Calculate the standard entropy change for the following reaction. And all the standard entropy values are given right there. Now, one thing you'll like about entropy is all the values for S are are positive. And you can find them in the back of your notes as well. So here's the one reaction. 2 NiS plus 3 O2 gas gives you 2 SO2 gas plus 2 NiO solid. It's very important that you look at the solid and the gas symbols, because what they'll normally do and what they can do on the AP, they can give you not just 4 values, but they could give you 12. They could give you one for nickel NiS, solid, liquid, and gas. Everyone they give solid, liquid, and gas for all of these values. And you only are going to use the ones that are in your equation. Okay? So the delta S standard entropy will equal 2 times the entropy of SO2 standard, okay, plus 2 times the standard entropy of NiO solid, okay, minus 2 again times the standard entropy of NiS, and 3 times the standard entropy of O2. Now remember, delta H of formation for O2 is 0. Any element is 0, but that's not true for the entropy. They do have values. So let's plug all the numbers in. 2 times, okay, make sure I do my math right. SO2 is 248. Plus 2 times, for NiO, it is 38. Minus 2 times, for NiS, it is 53. And for O2, it is 205. Now, all of these, I'm not putting the units here, are joule per mole Kelvin or joule per Kelvin mole, however you want to say that. And let me just do the math and get that here. Oh, Chalk is going to fall there. Okay, so 248 times 2, 496. Plus, the good thing is there are no negative numbers in entropy, so that makes it an easier one to calculate. 496 plus. Now you have the minus in the equation, though, to watch out for. 3 times 205 is 615. So, I sure hope I'll make a quick check on this, because I know it's going through so quick. SO2, 248. NiO, 38. NiS, 53. And O2, 205. And then 2 times NIS, 3 times the O2, 2 times SO2, and 2 times NiO. See, when I'm doing it in class, people can say, Vela, you just did that, in case I mess up something. All right. So that looks like 572 minus 721. And so 572 minus 721 equals negative 149. The unit is joule per mole Kelvin. That's your change in entropy, standard entropy change for that chemical reaction. And does it make sense? And let's just look at this for a moment, because look at this. Remember, look at solid, gas, gas, solid. Okay, ignore the solids now. We go from gas, 3 moles of gas, to 2 moles of gas. That means your volume of your system at constant pressure will decrease. It'll go down to 2. That means you're going to have more order, which means less disorder. So low disorder. You have a negative delta S. You can predict it from looking at the equation. It should be a negative value, and it is negative value. Hopefully I just did my math right, but I know it should be a negative number. Yeah, it looks like I did everything right there. Okay, so that's the fun. That's all you do. So do those 2 problems on the back of that, and you're in great shape. See you guys.